Ok, gracias personas por acompañarnos en una transmisión más de Bestias Proposicionales. En esta ocasión tenemos un evento muy especial. Tenemos a Michèle Friend, que nos acompaña desde la Universidad George Washington, en una colaboración especial del posgrado en Filosofía de la Ciencia con el proyecto de investigación Bestias Proposicionales. Ya saben, denle like, compartan, suscríbanse. Y pues nada, la caja de comentarios está abierta por si tienen preguntas. La presentación va a ser en inglés, entonces les agradeceremos que sus preguntas también sean en inglés para que guarden la mayor fidelidad posible y podérselas compartir a Michèle. Y pues nada, Michèle, welcome. Thank you very much for being here. Cheers.
On m'a dit que c'est le jour où on apprend le français, donc je vais faire mon discours.
Non.
C'est moi en anglais, s'il vous plaît. Alors, muchas gracias por la invitación, por el discurso en la lógica a UNAM. Es una universidad muy very precious university and a very prestigious university in Latin America, and it really is a great honor to speak here. And so I take it very seriously, and it's a privilege. And thank you for coming here on a Saturday. In many countries, it's not possible to have a lecture on a Saturday.
It's almost not possible here either.
Well, as you all know, impossibility is an interesting problem in logic.
We can do philosophy every single day.
We deal with impossibility. In France, it's impossible on a Sunday. Sunday, transportation doesn't work. Sunday, you spend with the family. So, and so the buses won't take you anywhere. You stay at home. So everything on Sunday closes. It's impossible. Okay, so thank you very much for having me, and thank you for coming. And I understand most of you are students in logic. Don't feel afraid to ask me a question, to clarify, or to challenge me, or to say, no, Michèle, you're crazy. This is okay. I'm used to being called crazy. So maybe take a chair over there because the slides are here. I'm afraid we don't have a projector. And Gabrielle will have the slides anyway.
Yeah.
And I will more or less read them out, except I can't read through the screen, unfortunately. So it's going to be a little tricky. But we'll work it out. Okay, so I wanted to talk about beyond validity and I can't remember what the title of my talk was. Beyond validity and consistency in logic. And I want to talk about logic in terms of science, logic as a service to science. Someone called Max Cresswell, who is a modal logician, he told me one day in a bar, in a pub, that logic can be responsible to one of three things. It can be responsible to language. This is the tradition of logic. How do we think in language? The second one is to mathematics. How do mathematicians think, or how should they think? And the third one is it's responsible to itself. So the Polish logicians, they're sitting around, they say, we have two quantifiers. Let's make a third quantifier, see what happens. Or we have two truth values. Let's make another truth value, see what happens. Or an infinite number of truth values, see what happens. So they don't care about mathematics, they don't care about language, they just care about the logic, and they do fantastic things. Here, I want to talk about logic in the service of science. And I don't want to talk about ideal science. In philosophy of science, very often we think about ideal case of science. And this is very far removed from how scientists actually work. And I've been in a chemistry laboratory last few years in France, and I talk to chemists. They don't work in the ideal way that philosophers of science think. So we're going to be a little bit more in touch with what they think. So the order of go, you can follow me on the slides. There's a little number here. There's about 16 slides, so you'll know more or less where I am. It's around the same time for each slide. We're going to talk about immediate and relevant I can't read it. Inspirations. Then we're going to talk about the particular problematique, the challenge that was posed to me and what was going on. Then I'm going to present to you a formal language, which is new. It doesn't resemble the formal languages you have been taught, but it's very simple. I'll write it on the board because I couldn't put it on the slides. It was too complicated and life is too short to work it out. Then we're going to talk about reasoning, because logic is also about reasoning. It's not just representation. And then I will talk about conclusions. And one of the last slide, just to push you a little bit, will be about artificial intelligence. So just to come up to date a little bit. Okay. So what are my inspirations? What is going on here? So I'm inspired mainly by three things. One is a book by Cellucci. I didn't bring it with me, unfortunately. It's a new book by Cellucci, published in 2022, about revising logic. What is logic about? And he calls for logic at the service of science. And he says logic, the way that it has developed, is really this mathematical logic, where we have syntax, we have semantics, we do lots and lots of mathematics on this, we compare models to each other. And he says we have to rethink this, because this is not how the scientists are thinking. And for logic to become more relevant to people's lives, and so the scientists actually come to our classes and listen to us and learn some logic, we have to make it relevant for them. So he says we have to rethink logic so it becomes a logic of discovery, where we can use analogical reasoning, where we say A is to B as C is to D. So this is sort of like metaphors, where we say, oh, there's a relationship between these, and I see the same relationship here. So, and this is how we very naturally think. So this is analogical reasoning. There are a whole bunch of other kinds of reasoning that are they're not really considered to be logic, but they are. And we need to sort of reintegrate those so that scientists can recognize what they are doing as part of logic. And the other just a funny anecdote, because how much time do I have, Gabrielle? Is it half an hour or an hour?
You have whatever time you want.
Okay.
So to leave here maybe about 14.
Okay. I don't have that much to say. Okay. But just a sort of funny anecdote. I was talking to a mathematician who was working on the real numbers, and he had a way of generating real numbers, and he thought that this got all, unlike Cantor's diagonal proof, he thought he got all of the real numbers in his system. And he said to me, and I don't use any logic at all. And I thought, oh, what do you mean by that? And I said, reconstruct. I'm thinking, okay, of course he's using logic. He uses the word and, he uses negation, he uses or, he uses if then, but he's not explicitly using logic. He's not using a formal logical system. What he's doing is calculating. He's calculating something out, but of course he's using logic. So again, there's a background sense of logic, which we'll see a little bit later, but there's the explicit formal representation of the logic, which is different. And we use that formal representation when you take your undergraduate courses. You train yourself to think in a very rigorous way. And is not ambiguous. And is and, or is or, if then is if then, negation is negation. It's all very simple. It falls into place. You learn this very canonical, satisfying, it's like doing a Sudoku puzzle. It finishes, you've got all the things in order, and it's lovely. So this is the logic that we learn, and of course later you're going to learn that there are other ways of doing things, that and doesn't really mean and, it means many, many different things, or means different things. If then is crazy, and negation is even worse. So we learn these things, but at least you know how to argue very rigorously in a sort of normal way, and that's a very good basis. And then you can learn the exotic things afterwards, but after, not at first. The other motivation, it comes from William Byers, who wrote a very nice book called How Mathematicians Think on Paradox, Ambiguity, and Vagueness. And he says that one of the triggering things in mathematics to make new mathematics is when you have a puzzle, when you have a problem, when there's ambiguity. Do you want me to write it on the board? Okay. So William Byers. Byers. And he wrote another book about science a little bit later called The Blind Spot. And it's about, again, how scientists think. And he says also that it's really out of the wonder in science, out of the curiosity when something is going not quite right, not when how you expect it, that's when science advances. So there are two conceptions of science. There's the science that you do in the laboratory, when you have the blood sample and you check, does the person have vitamin B? Do they have iron in their blood? Blah, blah, blah. And you report back and say, yeah, they have the right amount of iron. They have the right amount of calcium. They're missing some vitamin D or vitamin B or whatever it is. That's laboratory, a standard laboratory type of science. It's not the science of discovery. It's not advancing science. It's just confirming what we do all the time. When you boil water to make tea or to make coffee and you put your thermometer in, you just confirm water boils at 100 degrees Celsius. Okay, we know that, no problem. But if you want to do something new, you have to, it's the wonder, it's the tensions that really push the science forward. That's the other inspiration. And the third one comes from Diederik Baten's, and he has something called adaptive logic. So adaptive logic adapts when there's a problem. So the idea is you have what he calls a lower limit logic. And that's just the ordinary reasoning. Everything is going fine. You got on the bus. There's no problem. The bus is going forward. You're going to get more or less on time to your class. All the stuff that is okay and in any sort of procedure. But then sometimes there's a problem. There's an earthquake. Whoops. Am I going to make it to class? I don't think I should maybe go to class if there's an earthquake. Maybe what I should do is something else. So there's a problem, right? And then when there's a problem, you need another logic, upper, I think it's called level, we'll see the vocabulary in a minute, logic that takes over when there is, what's the word that he uses? We'll find out later. I have it on the slide, but it's either anomaly or problem or something like that. So this is when everything is going fine and everything is normal. Then you need a sort of strategy. You need to adapt because something strange has happened, and you get a logic to deal with a difficult problem. And it might be a different logic, right? So it might be paraconsistent. It might be all sorts of weird things. So those are my three inspirations. So what is the problem? So the problem that I was posed, this was many years ago in a philosophy of chemistry conference, and there's this wonderful woman called Olympia Lombardi. If you have a name like that, you can do anything. She has an institute at the University of Buenos Aires doing philosophy of chemistry. And she specializes in quantum chemistry. But she was worried about a certain problem in macrochemistry. And she sort of got me into the corner one day and she said, Michèle, you know a lot about logic. Find me a logic for macrochemistry. That is chemistry, that you do in your kitchen, the stuff, medium-sized dry goods, you're making your coffee, that's chemistry as far as I'm concerned. So macro level chemistry where you can handle the things, where you boil stuff. So problems in macrochemistry for the purposes of conceptual analysis. Welcome. So conceptual analysis is when you analyze what are the concepts that are being used and you deconstruct, you reconstruct, you try to make sense of the practice. So I looked around. I thought, okay, nice problem. And I thought, well, I'll look at category theory. I'll look at oh, sorry, that's a particular problematique. Sorry. Yeah, Olympia Lombardi, right. So I looked at dynamic logics, I looked at modal logics, I looked at all kinds of logics, and she was interested in processes. And most logic is interested in objects. The object might be truth, it might be falsity, right? And it's very static. Or if it's a modal logic, the sentences that are necessarily true, the sentences that are possibly true, and they're just true in a world, and it's all very static. A dynamic logic takes you from this situation to that situation, what happened, but the situation is about objects, and it's very static. It's not about processes. And in macrochemistry, what are you doing? You're boiling, you're mixing, you're distilling. Hello, bienvenido. And do you want the chair? Because I'll be standing. Okay. So things are moving, and how do we analyze that movement? So I couldn't find anything. So I decided I had to make something up. So I thought, okay, I have to scratch my head, roll up my sleeves, and think about this. What am I going to do? So I had to rethink things from a new point of view, and it was hard. My little brain was going, oh my God, what are you doing? You can't do this. And really think about processes as the fundamental thing and not the objects, not a static thing. So it took me about, I don't know, maybe 8 months to get used to this. And every now and then I go, oh, I'd have a nightmare. And I go, oh, no, I can't think that way. But anyway, so I managed to do something. But it's very simple. It's always very simple at the end. Do you want to just move these chairs? Okay, so I invented a formal language for processes in macrochemistry. As I said, let's leave that. As I said, macrochemistry is about medium-sized dry goods, right? So I take some flour, I take some eggs, I take some butter, I mix them all up in the right way, in the right proportions. I put them in the oven so it heats up, and then I make a nice cake and it's lovely. Oh, sugar! I forgot the sugar. So you put some sugar, and if you forget the sugar, oh no, it tastes horrible. so I get a surprise, right? So what do we do? So what is in the logic? First of all, we have substances such as flour, milk, sugar, butter, a little bit of cinnamon, something, whatever. Okay, so a bunch of substances that are stable. They're not exploding. They're not melting. They're relatively stable. Some of them might be liquids, right? Like eggs. Eggs. Yes, eggs. So they might be a little bit in movement, but not very much. They're macro stable, we would say, in the kitchen. We then have some operations. 1, 2, 3, and so on. Mix, put in the oven, put in a container, put in the oven. Leave for this amount of time at this temperature. Blah 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 blah. And we end up with stable substances at the end. Maybe I have extra egg left over, and I have maybe a little bit of milk left over, but I also have some new things, a nice cake, and maybe some burnt bit at the at the bottom, and so on. And they have stabilized again. So this is a process in macrochemistry. In real chemistry, you're in a laboratory and you have these fancy things and funny looking containers and funny colors, and you heat things up and you mix things up and you distill and you have them. So imagine your very favorite picture of chemistry. People are making all sorts of strange things. Hold on, how far do I get? Okay. And the problems in science arise from wonder and, wonder and uncertainty. So that comes from William Byers. So the reason I put the things in red at the beginning was just to make sure that I pick up all of the things, those inspirations during the talk, so that's why it's in red. So wonder in chemistry, we're going to use another color. At the end, you might get what is expected. I don't know if you can, yes, you can see that. Or you might get unexpected. You might think that expected and unexpected are the negation of each other. That depends on how confident you are about negation. Right? So maybe it's just not E. So I'm going to be conservative. I'm going to call it U. So again, you thought you were going to make a cake. You taste the cake. Oh my goodness, it tastes of radishes. That's weird. What happened? Or it exploded in the thing, or something strange happened, right? So it's unexpected. I thought I was following the recipe. I was doing everything right. What do you do when things are unexpected? You go back to your ingredients. Were the eggs okay? Was the temperature in the oven okay? Was there some weird pressure thing going on? Were the substances okay? Did I do the right sorts of things? Did I get what I wanted? Oh, no, it's unexpected. So remember, we were at this lower limit logic. We were following the recipe in the kitchen. We were trying to make the cake. And we got, sorry, I have to look at here. Here it goes. And we didn't get what we wanted. So here comes the fun part. So again, inspired from adaptive logic, we also have a notion of context. So let me get another color. So Baten tells us and Cellucci tells us that the context and the content, what's the difference? The context is the stuff that's surrounding. The content has to do with the meaning of what is going on. So that becomes important, and maybe we have to unpack those. So I add an operator. Operator, very much like a modal operator grammatically, but it doesn't function like a modal operator in terms of reasoning. So maybe the substances were not actually as stable as I thought, or the eggs were rotten, or the milk was sour. Maybe I didn't perform the operations properly. Right? Maybe I didn't actually stir as much as I thought I had stirred, or something dropped out of the sky and the little explosive thing came in and I stirred it in because I was watching my telephone. Oops! And that's why it exploded. And so I didn't actually do the operations correctly. Or maybe there's a context of the final substances which is not quite right. Or the whole thing. So I'm actually trying to do this at a very high altitude, or maybe at a very low altitude. So the pressure is very different, or the temperature is very different, or so the surrounding context might be, the whole thing was really, or I'm trying to do it on the moon. It doesn't work the same way. Right, so the cake started floating around, or in outer space, right? It's very hard. So who knows? So the overall context of the entire experiment was different. So that's this U over here. What is this thing? It's an operator, grammatically, but not in terms of reasoning. And it's open, so that's why I just have this sort of like a box. And it's an open box because as a scientist, we now have to unpack it and we don't know what's in it. It's like Christmas, right? You get a nice Christmas present, you unpack the Christmas present, oh, that's what's inside, right? What is the context? And what counts as the context for a scientist depends on their training, their education, the lost experiences that they had, what instruments they're familiar with, what procedures they're familiar with. So each scientist will have different ideas about what to unpack. One might be skeptical about these substances because they ordered some of the substances. I mean, chemists now, they have like a catalog and they get to order stuff. They say, oh, I want this much magnesium and I want this much copper. And so they order it from a particular place. They wanted to save some money, so they bought the copper from somewhere else, but maybe it's not quite as refined as they thought it would be. So they might be skeptical about this. So that's the box that they would unpack first. And other people, they're interested in the instruments. And they know that one of the instruments has been a little bit glitchy recently, so they're going to be interested in looking here. And then other people might say, yeah, but things sort of changed in the laboratory in between, and there was something weird going on. There was an electrical thing that, I couldn't get on the internet, so the electricity went down, so maybe this is why there's a problem. So they might be primed to think in that way. So different scientists will look at different parts, or others are going to have a more global view. So different scientists will unpack the box, and will choose different boxes, and will unpack in different ways in a different order. So again, all I'm trying to do is describe what is, I'm going to have to cheat now. Right, so these are the 4 context places, and the context is important for the initial substances, the operations, and the final relatively stable substances, and the overall context. Does anyone have any questions?
The context is always relative to each individual scientist, or can also function for some sort of tradición de investigación.
Research tradition.
So the context, the context really has to do with the process itself.
Okay.
No, it's separate from the scientists. The scientists are involved in the process, but how we think of the context has to do with the scientists.
Okay, then the context is a sort of presuppositions that are sort of above or beyond the scientific theory which is taking place.
They might be part of the scientific theory, or they might not.
Sorry, I'm just trying to imagine what is in the boxes. Maybe you can.
Right. So the default thing would be things like temperature, pressure, containers. So maybe you thought that the glass container didn't have a leak, but it had a leak in it.
Okay.
So there's substance coming out, right? Or if the temperature is very, very high, things happen in a different way.
Okay.
And if the temperature is very, very low, things happen, your eggs are actually frozen. so mixing them doesn't work properly. So it's normally temperature, pressure, and containers. But it can also involve other things. So the example that we'll be looking at is catalytic process. So where you have a catalysis, right, a substance that speeds everything up. So I'll come to that a little bit later. So that's part of the context. The content has to do with what is the meaning, what is going on. I wanted cake, and I'm getting something that tastes very weird or that exploded. That's not very cake-like. So I reject the output. This is unexpected. As I said, I expected cake. It's not happening. So that's the sort of content, and what you look at in the context, whether you check whether or not there's a problem in the glass that held something, or a problem in the container, has to do with your training, what you're used to looking at, what you think of, your imagination, a number of different things. It's term of art. So the formal language is only for representation. Logic started as a type of representation, and a lot of logic is just a representation. And then later it became a representation, or rather I should say formalizing is a way of representing things. Now, I haven't given you any axioms. I haven't given you any rules of inference. I've just told you informally, check these things out, check these things out, check those things out. If that's not working, then go to your context boxes, choose whichever one you want, unpack it. There's no rule of inference here. It's just very, very low level stuff. So no axioms, no rules of inference yet. Although there is a sort of lower limit logic that is going on anyway, because of course we're reasoning as we set up our things, as we put things on the table, as we start to do our mixing, as we turn the oven on, we are doing some lower level logical reasoning, just normal stuff, just the stuff that you use to get onto a bus in the morning, to navigate around a city, to do all the stuff that we do normally when we're using basic logic, right? So this is going on in the scientist's mind, even though there's no reason to explicitly say, oh, I then use modus ponens in order to put the substance into the cake pan. You don't need to know that you use modus ponens, you do that naturally. So this is the lower limit logic. So what do I say here? So there's no inference rules and conceptual analysis. So we get back to Olympia's question to me. Conceptual analysis is about such formally represented procedures in macrochemistry. So the conceptual analysis will have to do with when I'm given something like this. And notice, of course, in chemistry, the substances are going to be chemical formulas, right? So more or less, that's what it will look like. And the reasoning starts, the fun reasoning starts when scientists meet the unexpected. Oh, that's right, the word is abnormality. So the abnormality is that I said there. So an abnormality in Baten's thinking, or in the work that he and his students have done, tends to be contradiction, because he's really in sort of logic world and he's interested in computers and things like that. So, but in science, an abnormality is just something unexpected happened. It could just be a tension between what I expected and what actually turned out. It's not a contradiction in the logical sense. And what we're going to look at is not a contradiction in the logical sense. So where is it here? So unpacking the boxes means checking the context. And this again goes back to Baten's, who's one of my inspirations. Which boxes you choose first, what you notice about the context will depend on your previous experiences, your training, your education, the instruments you have at your disposal. So you might say, oh, well, I actually have a thermometer. I can actually check the temperature. Or I have a spectroscope, right? And I can check the spectrum of some of the substance. If you don't have the machine, you can't check that, right? Or it takes a lot of money, or you don't have the resources. So you check the things that you can check practically, right? You're not going, and if you have, and laboratories now, they work in a team. There's somebody who knows about the finances and is going to say, and I say, oh, I need a spectroscope just to check this thing. They say, Michèle, we don't have one and we don't have the money for that. So check something else instead. So something that we can afford to check. So we have to use our imagination, see if we can find something else that was the problem. So it also has to do with what resources you actually have. And we should take that into account even as logicians sometimes. Your inclinations and your imagination. So you might say, oh, I think that we did some time traveling, and I think we're actually at the bottom of a mine shaft. Okay, all right, so Michèle, you've gone completely wacko, and why is there a tree out there? Yeah, the tree's growing at the bottom of the mine shaft. you know, but there's light from the sun. No, it's not the sun. It's actually a whole bunch of neon lights, and they're just sort of shining down. And we say, okay, no, Michèle, you've gone crazy. We're not going to take your hypothesis very seriously. We're not at the bottom of a mine shaft. You know, come back another day when you're a little bit more sane. So it depends on your imagination. And different scientists, and the same scientist on different occasions, will be sensitive to different things and will form different conflicting hypotheses about what went on. Right? So if you've been primed, you know, I heard the other day that this scientist had a problem with such and such, maybe we have the same problem. Right? So it depends on what you heard recently as well, who you were talking to. So let me now come to a particular case. So the particular case is something that I did witness, and it's one that philosophers don't know about because it hasn't been published, it's not there in the literature, so it's a secret. But it's not going to be a secret for very long. And the scientists were genuinely surprised. Right? So this was an actual case of real surprise witnessed on the faces and the expressions of the scientists. And they had some sort of procedure in some sort of a machine. So they had some stuff in the machine. And these are scientists that are specialists in catalytic procedures. A catalysis is something that doesn't change itself, but it speeds up the chemical process. So the way I think of it is, have you ever beaten egg whites to make white foam? Mm-hmm. It's better to do it in a copper bowl. It's faster because there's a chemical reaction that happens. Mm-hmm. Right? So now, does the copper degenerate when you do this? Well, a tiny little bit, there'll be a tiny little copper fight, but that's not what's going on. It's actually an interaction between the surface of the copper and the egg whites, something in the egg whites that actually makes the egg whites become bubbly more quickly. It's the same thing and so the copper itself doesn't change very much. I mean, after 100 years, yes, you're going to get a little bit thinner copper bowl, but it's going to be 100 years of beating egg whites. So it's not that's happening. So catalytic procedure is one that speeds things up and doesn't deteriorate very much itself when it's doing the speed up. These are all natural processes. And these things are important, especially for industry, because they want to do things a little bit faster than the natural process. So if, for example, you want to extract methane from biomass, you can add certain things in certain proportions so that it happens a little bit faster. Naturally, it will happen anyway, but to collect the methane is not going to make any sense. And tropically, it doesn't make any sense. It's too labor intensive. So you need to sort of concentrate things, get them in a pot, make sure that you get all of the methane to concentrated. Then you can use it in order to burn something, in order to make heat. So this is what they're interested in, and they thought, okay, and you have your catalytic stuff, right? And they thought, why don't we add a little bit more of the catalytic stuff, and then we'll speed up the procedure even more. It didn't happen. It actually slowed it down. And they were surprised. So what do you do? Now you have to form a hypothesis. So they checked all of this stuff. They checked the substances, they checked the operations, they checked the substances again. That wasn't the problem. So it has to do with the surrounding things. So they thought, well, we added more catalytic stuff. So we put more copper, we have a bigger bowl of copper, and it takes actually longer to beat the eggs. That doesn't make any sense. Right? So now you need the imagination and the training of the scientists to solve the problem. What are they doing? So this is the fun reason. Let's see. So it turned out that so they actually found out in the end that you had to have less catalytic stuff. So there's proportions, right? There's a proportion of stuff being converted to catalytic medium. It's a different thing. And there's a proportion of this stuff. And it's not necessarily the case that the more of this you put, so what, I mean, the hypothesis is if you increase the catalytic stuff, then you're going to increase the speed, and at one point it won't make any difference. Right? It's going to follow this kind of curve. But it wasn't doing that. Right? It was actually, so they added more stuff and it went down. That's weird. So they actually found out that there were optimal proportions that were smaller than they even imagined, than they even started with. Smaller proportions that actually made the thing go faster. So that was odd. This is new in science. It was surprising to them. So that was the real case. Does anyone have any questions so far? Because you're not chemists, so you don't. I had to learn about catalytic processes too when I went to France. And so what is this thing? So also they use, the biochemists, they'll use enzymes, for example, to break down plastics. Now, there are thousands of different plastics out there. We make well over 1,000. There are hard plastics, there are soft plastics, there are malleable plastics. There are ones that can withstand very high temperatures and so on. So they're all different. One enzyme can't eat all of them. So and how many enzymes are there? Thousands of enzymes, thousands and thousands of enzymes just in nature, right? These are the things that are in your saliva that break down some of the food, right? And you find it in your stomach as well. They break down some of the food. So it's something that's natural, it's bio. And if you there are some enzymes that can actually break down plastic. And breaking down plastic is complicated because so plastic is a whole chain of different things, or polymers that are MERS, the MER parts are poly, so it's lots of them that are linked together. And the breaking down means breaking those chains into smaller chains. But what they really want in industry is to break it down to the very, very small parts, not even nano parts, but individual parts so that they can reassemble and make something else. And this is part of what they call circular economy. But it's not simple because the enzymes might just break it down a little bit, but not enough to become useful again for industry. So recycling plastics is non-trivial. Okay, so that was sort of a break in the thing. So conclusion, I have 3 conclusion slides. I'll talk about very different things. So in the case presented, the result was counterintuitive, right? We expected that curve and we got this curve. It wasn't contradictory, but I wanted to use it, and I wanted to use a real example that you might not know about. So what happens when we're forming that hypothesis and we're finding a solution? This is when we move to our upper level logic, because we found an abnormality, something we didn't expect. So we move to our upper level logic and we reason that maybe this is not the right curve. And that takes imagination. So what is the scientist doing? He's thinking a little bit outside the box. He's willing and courageous enough to ask the question, maybe this is not the right curve. Maybe we have to rethink our theory. So what logic is the person using? And we can also imagine laboratories where the scientists can't work this out. When you have some mathematics, it's sort of interesting. When you have mathematics, people become really wedded to the mathematics. They love that curve. They're not going to give it up easily. it's really hard to think, oh, what happened here? It's a problem with what I expected in the curve. That's really, really hard for scientists. And they don't really think about it because they're not consciously, they don't do philosophy of mathematics, because they all should do philosophy courses. And then they would become more flexible in their thinking. And these scientists, because they had a lot of experience, they were able to solve the problem fairly quickly. But we can imagine problems in science that take much, much longer. And we can imagine real big contradictions, such as when Lavoisier was thinking about atomic weight as being the most important thing about chemical substances versus the people that believed in phlogiston and phlogiston theory. They organized chemicals in a very different way. The battle, I mean, you're all taught there was this chemical revolution, and then everything changed. It took a long time for things to change. It was very political. There was an institute. Certain people died off on the phlogiston side, but conceptually they were actually kind of on a par, because of the people doing atomic weights. Lavoisier, he had really spooky things too. And phlogiston is kind of spooky because we didn't really know where it was, and it was this kind of a substance that brought heat and sort of did something weird. And when you did electrolysis of water, you had dephlogisticated water and you had phlogisticated water. So it just had more of this thing, whatever it was. Now we think of that as hydrogen and oxygen, which are very different substances because they have different atomic weights. And so it took a very long time. And on the atomic theory, they also had something called caloric, and they had lumière, light. Yeah? So, and those are metaphysically just as spooky as phlogiston. So conceptually, the two theories were on a par for a very long time. We have now gotten used to the periodic table of elements, and we've gotten used to that, but it was not an obvious switch for individual scientists. It was not an obvious switch for students. There was a lot of tension, and conceptually it wasn't simple either. The reasoning was not very simple. So because the reasoning was not very simple, one has to go to non-classical logic and sort of exotic logic. So this is a motivation. If you want to rethink logic, so remember Cellucci was saying, let's do logic at the service of the scientists. How are they actually doing the reasoning? Well, how are they unpacking those boxes? That's a fun bit. And they might be using something like a discussive logic, where you have a discussion between different people in the laboratory. The administrator who says, no, Michèle, we can't afford one of those fancy machines, they're really expensive. Or we can't do the experiment with 1,000 different plastics and 16,000 different enzymes. We don't have the time and the personnel or the space. You can't do that. We have to find another way to find what it is that breaks down different plastics. Let's use a computer program. Let's use an artificial intelligence to try to bring down the number of choices that we have. So they have to think a little bit outside the box. Thinking outside the box is something that classical logic has difficulty with. It's very open, but it's also not prompting and enabling of giving you a direction in which to think, whereas other logics sometimes are better adapted at doing that. Okay, so second conclusion. So again, this answers Cellucci's call, right? Cellucci called us to rethink logic. What is the role of logic? It should be at the service of science, or at least some of it should be at the service of science. We should be willing to embrace analogical reasoning or discussive logics or paraconsistent logics in order to think about what's really going on in those scientific tensions. When we are discovering, we are making hypotheses, we're finding solutions to problems. Olympia Lombardi asked me to find a logic to represent, and so her notion of logic was not what you're trained in thinking about. Representation was already enough. logic to represent reasoning in macrochemistry for the purposes of conceptual analysis. So the logic that I've given you, so again, I haven't even told you what your upper level logic is. I think that's going to depend on the situation. It's going to depend a little bit on what you want to do. Personally, at the moment, I'm favoring discussive logics because they don't have a particular formal logical representation. I mean, there's different ones, but the idea is that you have people in a laboratory that are negotiating, what should we do next? We got a weird result, what should we do next? We could pack up the project and tell the funders, oh, cut off our funding because we didn't do what it is that we wanted to do or that we promised that we would do. Or let's try to keep the funding and find a way out of this, find a solution to the problem. So and then what is a good way of honing or managing that discussion? So it's one thing. So part of the investigations I've been doing recently is in things like system science and solving problems in democracy and solving problems, negotiating real life problems where you have conflicts, political conflicts. And it's one thing to say, oh, as some philosophers do, just get everybody into the room, and if they talk for long enough, they'll start to agree. Not really. They might kill each other. So it doesn't happen that way. What you need is a catalyst. You need somebody to direct the discussion, to say, look, there are certain things that you're allowed. There's a protocol. You're not allowed to hit each other. You're not allowed to insult each other. This is not what's going on. You have to speak in certain ways. You're going to be given certain amounts of time. One person doesn't get to talk to 3 hours and yell and etc. while everybody else stays silent. There are certain protocols, and you need someone to kind of mediate and direct the discussion who is neutral on the outcome, or relatively neutral on the outcome. And this is where system scientists and certain types of negotiators are very strong, right? They'll bring people together. The way that I do it is I don't bring the people together because I think even that energy can sometimes be too much. But I discuss separately with the different people, and I say, I do the negotiation between them. What can you bring to the table? And sometimes that's a good way of doing things. What can you bring? So we have a discussion about what is it feasible for you to do? What are you willing to do? What are you willing to be committed to? And are we all then going in the same direction? So you're actually complementing each other, and you don't even have to know, right? You don't even have to know that you're helping your enemy, right? You just have to know that you're doing something towards a direction that you want. And each person individually can work in a direction that they want. So the discussion has to be mediated. It has to be guided by someone who's got the tools and the imagination and the neutrality to do that exercise. So again, and then discussive logics, I think, are going to be able to help with that part of the solution. Where am I? Blah, blah, blah. This is and this idea of the lower limit logic, which is where the scientists are thinking anyways, then they get an abnormality and they move to the upper level logic. This is using Baten's adaptive logic. So I'm combining different logical conceptions or logical frameworks together. So in conclusion, so this is the provocative bit where you're going to go, oh gosh. So what if we ask an artificial intelligence to help us with the unpacking? So we call up ChatGTP and we say, unpack that box for me. What's going on? Right? So it too will use an algorithm, right? They're just computer programs, to look at past experiences of scientists, but it's going to look at the past experiences of scientists that it has access to. What does it have access to? What is on the computer? What is on the internet? What is on the World Wide Web? It doesn't have access to the conversation that I witnessed between the scientists where they were saying, oh, we put more catalytic substance in there and it didn't go faster. It didn't obey the curve. What are we supposed to do? And they were rethinking. The AI doesn't have access to that. This happened there was no CCTV camera capturing what was going on. So it doesn't know, right? So there's a lot of informal stuff in our education that ChatGPT doesn't know about. Furthermore, when we publish in science, we tend to publish these successes. What are the results that we got? And recently, I also witnessed another conversation that ChatGPT can't access, which was about how to write papers in science now, especially in chemistry. Chemistry is a very, very fast evolving field, right? It's moving really, I shouldn't have used the word evolve, changing field, right? So a lot of stuff. We've made thousands and thousands of chemicals that are artificial and they're in nature. Thousands of them. And we're just making more and more and more. So, and ChatGPT, so when chemists write a paper now, we used to write papers in science that told a story. What is our motivation? What is the project? What are we after? What's going on? What is the context within which we're working? What is the type of solution that we're looking towards? Not anymore. You read a modern chemistry paper, they will tell you, this is the methodology, these are the instruments, these are the results, period. List of results. They might organize the results, right? They might say, these are the results having to do with enzymes with this kind of plastic. These are the results of enzymes with that type of plastic. These are the enzymes that do that kind of plastic. That's it. They don't tell you why. They don't tell you why they were looking at that. They don't tell you about how they were unpacking the boxes. So ChatGPT doesn't know very much about unpacking those boxes because it's not available to, nice little ChatGPT, sorry, it's going to now explode. Now be careful, it's political. So it will converge to a most likely solution because it's going to have lots of graphs, lots of results. It can crunch the numbers. It can look at a lot of stuff, a lot more than we can, but it doesn't have available to it that imaginative part. It just has the results. And it might even be able to weigh this against resource costs, right? So you might say to ChatGPT, sorry, but we can't afford that machine. We can't do that. Find another way of doing this. And it can, that's why it's intelligent, right? It can do that bit. And it will converge in what I call a dumb way. Dumb, I'm not using that in a political sense, I'm using that in a technical sense. That is, it will just converge in a very algorithmic sort of way, right? It's been programmed to do certain things. In fact, if you put two artificial intelligences together, two ChatGPTs together, and you get them to talk about some topic, the intelligence will start to go down. This is very important. They reinforce the lowest common denominator between them. So you don't get that imagination that you need from humans. You don't get that spark. You just get the more and more generic, more and more, and they want to converge on something. That's what a conversation is about. So converging tends to be sort of the most general, the most generic sort of way of thinking about something. So that's all that, so they can handle large amounts of data about the scientific experiments in the past, but they won't be able to, so if we ask an AI to help us with unpacking this or unpacking that, they are very, very good for the data crunching part, but they're not very good at the imaginative spark and the thinking outside the box is a nice expression given the box operator. And so they won't be able to use the proportions of data in a relevantly discerning manner. So again, think about the data that is available and the quantities of data. So quantities of data, if you've got a laboratory that's doing a lot of stuff on this, it's going to think that's what's normal, right? That's how it's going to reason. So these results are the most important. They're the normal things. It doesn't know how to count. There might be a tiny little laboratory over there where they're not doing very much, but conceptually it's much more significant. It's much more interesting. But all it does is it takes, they've got 3 results. They have 40 results. That's only 3 out of 40. So they don't matter very much. So their statistical reasoning it's good statistical reasoning, but it's not very discerning. It doesn't say, that's really more revolutionary than that. You can't tell the difference. So it's going to deal with large proportions of data, but not in a relevant to the particular problem, not in a relevantly discerning manner, and will fail with imagination. And so the effectiveness of using artificial intelligence in laboratories to help scientists, it will go up at first. It'll be very successful at first, but it's going to then plateau. So it's going to follow our favorite curve again, right? It's not going to bring in that spark of imagination. So that was just to plant those seeds of thought. So that's good for now. I think that's good food for thought. Cakes being not having exploded, so we can't eat them. So that's it. Thank you very much.
Thank you, Michèle. Now we've got some time for questions.
Thank you. I want to think that this is not a presentation about a instrumental view of logic, or yes.
It's a very wide view of logic. And instrumental means different things. So I'm putting logic as an instrument for chemical thinking, or more widely for scientific thinking. Philosophers of science, when they do philosophy of science, they tend to think about physics, or they do philosophy of biology, so then they're interested in evolutionary theory. And philosophy of chemistry is a really small group of people. And chemistry is not non-science. So what I'm thinking about is putting logic as an instrument for the scientist to use. Am I thinking instrumentally in the sense of fit? That this is a good logic for this situation, for this kind of problem. Yes. So that's a pragmatic element, for sure. And what counts as fit is kind of so that's also a little bit of a term of art, right? Because I can use any logic for any situation, any logic, any formally represented system for any situation that I like. However, it might not be very good. So I can speak in ancient Greek and try to fix the computer. It won't be very good because the words are not there. And logic also, formal logic, is very rigorous. There's no deviation, there's no ambiguity, it's not vague. And that's the beauty of the logic, right? There's something nice and it just draws you along. But there are certain things it can't see. And if you're caught up in the logic, sometimes there are things you can't see. So you might say, well, too bad for the theory, too bad for the experiments. They're just not logical. So there's nothing I can do. So you need to find a logic that's actually going to help you to solve the problem. And solve the problem in a way that the scientists say, oh yeah, that is a solution to the problem. As opposed to saying, sorry, you're being illogical, stop your science. Scientists are going to say, okay, but that's not the kind of solution I wanted. Right? or what you should do is just blow everything up, and then you have a solution. Well, again, the scientists might say, well, that's not really a solution the way that I count it, right? So which logic you choose and what will fit the situation well. That is a type of instrumentalism, if you like. I'm not sure if that answers your question. I always find the word instrumentalism a bit weird, so maybe you want to tell me more about what you mean.
Okay, yes, instrumental like now logic. We take logic to check and make some results, and everything is good. So logic is it's for use. It's
Right.
As a tool for science.
Yes, very good. Very good.
Okay.
Exactly. And that's exactly what Cellucci was asking us to do, is stop as logicians. I mean, it's a little bit political too, right? Is that Cellucci is saying, look, you logicians, professional logicians, you're doing lots of beautiful, fantastic, lovely stuff in your mathematical logic in particular. That's what he picks on the most, mathematical logic. Oh, so let's put another mathematical sort of spin on this thing. And they're sort of constructing all of these logic stuff, but where is it useful?
Okay.
And Cellucci is saying, let's try to use logic to serve science. So yes, exactly in that sense, is bring it back down again. Just as the universities, we were talking informally a little bit later that the university, one model about graduate work is to get you more and more specialized. So you become, the top thinker in this one area, and you get your PhD because you're at the end and there's no one you can talk to anymore. So
No, I understand.
that's right. Or maybe you can talk to your supervisor and your examiners. Yeah, but even they don't know what you discover. Not really. They haven't really thought it through the same way as you have. That's what the PhD is about. And that's not back in service to the community. That's not to serve the person on the street. It's not to serve your parents. It's not to serve your family. It's not to serve the Mexican people. It's just to get one edge over. So that's one concept of university education. And that's very prevalent in the United States. It's prevalent in the Anglo-Saxon world. It's a little bit different in France and Italy and Spain, but not much. Is that you want to get to the edge. You want to, research should be new research, and it should be beyond anything else. And then you've done your job. Finito. I've done my responsibilities. I get my pay. I'm done. And now I get a job, maybe, if somebody actually wants to find out about this weird thing that I did. Another conception of what is the university about? It's about teaching people, bringing concepts that are useful, that they can bring back into the community, that they can serve the community, that we can learn how to, and it's political then, how do you serve other people? So one of the universities I'm very involved with is called the University of the District of Columbia. It's right in the middle of Washington, D.C., and they have a whole faculty of agriculture. Agriculture in a city, what are you talking about? Agriculture is outside in the fields, not in Washington, D.C. But it is in Washington, D.C. They have community gardens. They have food trucks. People in Washington, D.C., they live in what we call food deserts, where they can't get lettuce, they can't get fruit, they can go to you can always find a gas station in the United States. So you can always get chocolate bars, you can get chips, you can get junk food, you can probably find milk as well. But you might be able to find an apple that's not very happy with life anymore and sort of, travel way too much. So there's apples, but not really. So poor people can't afford to take the bus to take them to a shop where they can actually buy good food. And if it takes too much effort to get good food, then you live in what's called a food desert. And some rich people live in these as well. Why? Because they have a car. They get into their car and they drive and they go to the grocery store. They don't walk to the grocery store anymore. And other places, there are lots of little community. There's a butcher's, there's a greengrocer, there's a place where they make bread, and so on. So you can get everything within walking distance. And in Europe, that's very important. So there are different conceptions about this. But the University of the District of Columbia, they do urban gardening. So they take places and they grow the vegetables, they grow the fruit in the area, and they teach people how to do the gardening. And they also do sort of artificial gardening, where you do it through indoors because it's a little bit cold in the winter, so you can't get fresh vegetables that are grown naturally. So you do them in a sort of you do hydroponic gardening and that sort of thing. And they teach people how to do this, and they enable community, and they also teach them about nutrition and how to cook, and they bring food around to people who are living in these deserts. And it's just, they're using all of their knowledge and their expertise and their engineering and their thought about agriculture to serve the community around them. And it's directly connected. So this is another conception of university. What's it for? So I think that the concept of university is also changing. And I think it's coming back to this idea of how are we serving the community? Who are we serving with this knowledge? And if you do some very exotic, lovely, complicated logic, Cellucci is going to tell you, sorry, but serve the scientists. Now, the scientists, too, might be doing something very exotic that doesn't serve anybody, right? They're doing something about, fundamental particles that is going to take a long time before that's going to serve somebody who's a cleaning person in a hospital, right? It's not going to serve them. Not for a very, very long time, maybe. So the question is, let's take responsibility for what it is that we're learning, beautiful as it is, and wonderful as it is. And maybe also as researchers, we need that time to explore the very pure stuff, to get rid of all of the white noise, to just do the very beautiful, exotic, hard, technically difficult things, to hone our minds. I mean, I did this for a long time. I escaped reality, right? I was sitting in my office, I kept my hands clean, I did the really, really hard stuff. And I needed that to now have the strength to do the political things. So but I want to do the political things now. And I feel that responsibility. But not everybody's ready to do that. So to sort of punish people right away because they're not ready to do the politics, maybe, give them a break. But what is the university for is an important question. And now that there's a crunch on resources, the planet we're facing a kind of big existential question. What are we doing on Earth? What are we doing this for? And the chemists I was working with were very concerned. They're making these plastics. They're talking about biodegrading the plastics. They're talking about biofuels and how to catalytic processes to speed this up. But at what cost? What is the cost? Do you need to bring in new material? So one of the conceptions is circular economy. Have you heard of this conception? So household waste is terrible. There's too much different stuff in it. And we do a little bit of sorting out, but it's not good enough and it's a nightmare. But industrial waste is kind of easy because it's in one place and it's one kind of waste. There's not as much variety. So an industry can take the waste that it has, put it somewhere, get a few machines, put in some energy, maybe bring a few other things in, and make a product that they can sell. So they make money, they're happy. If they don't make money, they're not happy. So they're not going to make a product just to distribute to the poor communities, no. But if they make a product that they can sell, then they're okay. But they're using their waste that they have there anyway, and instead of putting it down the drain or sending it in a truck or incinerating it themselves, they can now make something out of it. But to make something out of it, this is what everyone ignores in the circular economy, you had to bring some other things in. you had to add energy. Where did the energy come from? Where is the other stuff coming from? Is it coming from a mine in Africa where the political problems are really bad, where the health problems are really bad? Is it worth it? And maybe it's not worth it. So, and that was some of the work that I was doing and that's a philosophical question. And it's not something that there's an easy solution to. What's worth it in one context is not worth it in another context. It makes sense to do biofuels out of sugarcane in Brazil. Why? Because they grow lots of sugarcane. You try to make biofuels out of sugarcane in northern France, you know how much sugarcane you're going to have to move across half the globe? It's not worth it. But so make it out of sugar beet, because they grow it there. But there was a problem a few years ago that the sugar beet was being attacked by some sort of a pest. So they wanted to spray a pesticide, but the pesticide would kill the bees. So then you don't have your pollinators. So there was a discussion in Parliament about whether or not the farmers were allowed to put in this pesticide. It was decided that they could, but the cost was the bees. And so these are what I call complex problems. These are the kinds of problems that we're going to face more and more and more. And it's going to take philosophy to solve these sorts of problems, or system science, or something that can deal with that complexity of there's politics, there's economics, there's emotion, there's resource problems, there's our cost to the environment, how much are we destroying it, which parts of the environment are we destroying, how much is it worth it, who are we? And that's the existential question. So it's all kind of wrapped up. Other questions? Yep.
Yeah, well, I know you told us from the very beginning that you weren't going to deal, at least not very deeply, with inference groups. With this knowledge, but I like to push a little on that direction.
With what? Sorry, inference groups?
Inference rules, sorry.
Rules, yes.
Yeah.
Okay, yeah, sorry.
Insofar as the trouble seems to be to account for the unexpected within initially deductive framework, well, it seems pretty natural to me to think that to find out what might be inside those content boxes needs of some sort of to frame it within an explanatory context, which needs of some sort of adaptive logic.
Absolutely. Yes, exactly right.
Well, and my question is, what would be that logic? Which kind of operator needs?
There are several of them. The people who are most advanced in analogical reasoning, there are computer scientists that are in Toulouse, and they've got a very, very nice way of dealing with this, and it does bring context in, and what you notice in the context. It's actually very sophisticated. I don't have the rules in my head, I'm afraid. And I don't even have their names off the top of my head. You'd have to look at Toulouse, France, computer science department, analogical reasoning, and then you would find out. And they have several systems. So that's a very nice one. And then if you're dealing with with different people that have different hypotheses, different ways of doing things, different strengths in a laboratory, normally this is the case. Then the discussive logics that are done in Poland, I think, and again, there's several of them. But the idea is that you have different people having a discussion, and there are rules about how they have the discussion. And what happens when they have a conflict against each other.
Okay.
Right. So there are rules about what to do with contradiction would be one way of putting it, but it's not. It doesn't have to be as strong as a logical contradiction. So how do you conduct a discussion when you have different points of view?
Okay, more words, yeah.
So there are lots of, in other words, the rules of inference are lots of packages. and packages of logics that are supposed to represent reasoning, and you just pull them from, they're available.
Okay.
So one rule might be, well, A is to B as C is to D, if and only if, and you have to be able to see what are those relationships between the two things, and what is the class of relationships you're allowed to look at. So you have to then, so you mathematically or logically, you describe those relationships, and then you have to pick out, is one of those going on? Now you might have missed a whole bunch of relationships.
Okay.
So same color as would be a relationship, but maybe that's not pertinent to what you're doing, or at the same temperature as, or has the same number of ions would be something in chemistry, but this has the same number of ions this substance does as that one does, which is the same as these two substances also have the same proportion of ions, same ions.
Okay, I understand an analogy in a broad sense as translating a problem into some other context in which the problem is easier to solve, or at least, well, yeah.
That's right. So this is
That's not exactly abduction, isn't it?
It is a bit. So, again, how you characterize abduction, so inference of the best explanation, what counts as best, depends a little bit on the person, depends on your logic, depends on what you see and what you don't see. And best might be best in the short term, but not in the long term. Right? So, especially in political negotiations. So as I said, what's important with these discussions is that they are mediated, that there is someone who's playing the role of catalyst in the group, who is making sure that things flow, that you are converging towards some sort of solution, and it will be a good sort of solution. And that takes it's a type of reasoning, which is very dynamic reasoning, that has its rules and has different sets of rules. And those rules are used in order to guide, in order to make sure that things don't go off track, so that you stay with relevant considerations. You don't go off track and start talking about something else. So if you arbitrarily get people into a room and you say, oh, discuss for a long time and you'll all converge on an opinion, it's not going to happen. You'll converge on something that has nothing to do with what you're trying to solve in the first place. So you need, I really do believe that we need discussions, especially when there's tensions. You need for those discussions to be mediated. And the people that I know who are very good at this are system scientists, not so much philosophers, because we work on our own. so we're not any good. But the system scientists are very good at that sort of thing, because they're looking at the whole system, on the relationships between things. And if you want a logic, then a discussive logic or an interactive logic is actually quite good at doing that. So this consideration is too strange. We're going to push it away. Nobody else agrees with it, so let's push it out. So that would be a sort of rule, is that nobody else in the group agrees with this. You either have to further justify it, or we're going to get rid of it. You don't get to bring it up again. Would be a type of rule. Now, if it's a good rule, I don't know. So.
Yeah, well, that will be in the context of testing that a later explanatory hypothesis. Mm-hmm. But I guess I'm more concerned with the inferring of the hypothesis in the first place, as a part of the sort of logical scientific discovery.
Mm-hmm. Mm-hmm.
Well.
Yeah, I don't know. is the fast answer. If we could find that out, then we wouldn't have to have PhD students anymore. So, because it really is. People have asked me, how do we guide PhD students to getting a good topic or getting a good solution to a problem? I don't know. I mean, it comes really from your experience, from your imagination, from what the student is able to do, where the student's interests are. So this is something that is very personal. It's not, you can't get a logic that does that for you. No, I think. And that's why the artificial intelligence isn't going to necessarily, I mean, they might come up with interesting things, right, at first. But at some point, it's going to peter out. It's not going to be very interesting anymore. Yeah.
Exactly, I was going to ask about the artificial intelligence. I was thinking of logic as a tool, just as a tool. What about if I feed the artificial intelligence with certain kind of logics or certain kind of maths?
Yeah.
And then I pre-train it to choose the best tool for whatever I'm doing.
Right.
Is it going to in some way take away the work from the people who is imaginative and inventive, and because the artificial intelligence, I think that if we see logic as a tool, can do.
Yeah. No, that's a nice question. I think because you might feed it a logic that is not non-standard, that it hasn't been fed before, right? It can help you write the logic, the program, right? In order to give it a lot, so give you the rules of inference, where you have the rules of inference, and you ask it how to express that in the languages that it knows. So you can, that's a very nice approach too, is to give it certain ways of thinking that are maybe different from the way in which it normally thinks. So for example, as I said, of statistical reasoning, right? You say, oh, there are 3,000 results in this area, but only 3 in that one. Therefore, this one we don't care about because the number is really small. Well, let's give it a little bit better sense of imagination and tell it how to notice that these things are actually significant, that they are important. How you're going to do that is going to come from you. It's not going to come from a logic program. It's not going to come from a formal logical system. So, and I don't know that we can, it's a little bit answering your question too about how do we come up with a hypothesis? And it might look like a hypothesis, but it's not, it's actually going to be the end of an algorithmic calculation. So it's not going to be generating a hypothesis, it's going to be coming up with a conclusion. So it's a little bit, the flavor is different, even though it might look like a hypothesis. So it's interesting, and maybe that would be the way to go too, right? Would be to make the intelligence a little bit more intelligent and a bit more imaginative. So right now, ChatGPT is supposed to do 10% original, and original means anything you like, right? It's just got to put stuff together that's grammatical. And it really is complete nonsense that comes in sometimes. So it will even make up things in your bibliography that don't exist. And all it does is it copies the format of a bibliography. It makes up the name, it makes up a title, it makes up a publisher, or copies part of the publisher, whatever. This was done by Springer, and you look it up, it doesn't exist. So, and that's original and imaginative. It's not. All it did was put different bits of syntax, strings of letters together or words together such that it makes sense grammatically, but that's not imagination the way that we want. That's not going to come up with your hypothesis except by mistake. So what we want is the discerning part. And the logics, different exotic logics or slightly deviant or weird logics, might be the sorts of things that will guide the artificial intelligence to come up with something more really intelligent. So that's a nice suggestion. Yeah.
I have a question.
Yes.
Well, it's a little bit complex. But I trying to make a synthesis because I had a lot of things that I need to say. Well, after this, you say about the role of the university in community and society. I think that if you if you need to answer the question about what is the role of logic for science, you need to question about extra logical and extra scientific aspects of it. For example, not only what is the role of the university or who they made it who they made the research programs and what are the intentions. Because if you shouldn't take this aspect, you only can give an very general answer. For example, that it's mainly for representation. Mainly for representation.
Right.
So, well, I don't know. I like it, but it's partially unexpected because no one can accept that we need to take extra scientific criteria or extra logic criteria.
Is your question about thinking about all of these things at once and how to put these things together? So how do we even recognize that how the scientist is thinking? And then as logicians, we don't just represent how they do think, but we want to represent how they should think.
No, only.
Okay.
I think if you think if you need to respond on this as well, let's my answer after you talk is maybe it's a little bit meaningless for this. This is the reason because as the answer is relative to a context. So there's no if you want to know what is the role of logic in science, what is the what is the role in this particular research?
So I'm going to turn the tables on you. And I'm going to say that it's really within the context that you get meaning. You don't have meaning outside of a context.
Yeah.
So I just reversed the thing, is that is the thinking that we need, is the thinking within context and to recognize context. This is very, very important. And that's something that logic is sort of funny, right? So if you learn just classical logic, you're sort of doing the logic God is doing. It's the way of seeing everything. It puts an order on everything. But it doesn't, the logic can't recognize, so what is meaning? What makes things meaningful? It has to be meaningful not to God. I can't understand God's notion of meaning, but I can understand meaning for me. And meaning for me is a little bit emotional. It's a little bit that I feel that there's something going on. I feel that I'm making sense. I feel that something meaningful is happening, means that there's a little bit of emotion there. And the emotion is not God's emotion, it's my emotion. So for the scientists, it's for them to make sense. So when the scientist says, I'm coming up with this hypothesis, and that's going to make sense to me, it's the logic in the service of the scientist. And that's very context specific. Exactly so. So, and that's when the meaning comes in, because that's when the feeling comes in. So yeah. But good question, thank you. It's fun.
Thanks for you.
No, and you're quite right that it, somebody might say, look, Michèle, you're not doing logic, because logic for us is logic that how does God think about science? God doesn't need to do science. God's the one that invented science. So that's not the problem. So the science is our science. It's for us to make sense of what's going on in the world, for us to understand, for us to progress, for us to do things that are worthwhile doing, and for us to understand that we're doing and notice that we're doing something that's fun or interesting or meaningful. So the science is our science. So that context is important too. Yeah. So I like the question. It's good.
Science in a context.
Yes, yeah. Good. I think you're hesitating. Yeah.
Some questions. First of all, thank you very much for your talk. I really like. The first question is about what is the role of pure logic in this kind of enterprise? I think is important, but maybe not central. Can you tell us about?
Okay, so let's ask the question: what is a pure logic? So a pure logic is supposed to be topic neutral, in some sense universal, whatever that means, and often divorced from content. Now, what do we mean by content? Now, we might mean semantics, but as soon as you have truth values, you have semantics. So if you're doing a pure logic, you've got to say something about your truth values, or you're doing proof theory, in which case your semantics and your syntax are together. They are wedded, because what are you doing? You're preserving knowledge through your proof. Now, if you're preserving knowledge, then that's pure in the sense of you're not in, you can do the calculation, you can do the proof without thinking too much about the knowledge that you're gaining, right? So one way of thinking about it is you have, so what does the pure logic do? So we have our question. So we have premises, and we wanted to get to some sort of conclusion. Okay, fine. And we don't always know what the conclusion is going to be, right, in advance. So if you're doing proof theory, you don't always know. If you're given, give me the proof from these premises to this conclusion, then I know already it's a valid proof, right? Otherwise, I'm sadistic if I give you, as students, I tell you, oh, prove this conclusion from these premises, and you can't do it during your logic. I'm not sadistic. So I already give you one that's valid. But so the question is, how do I get from there to there? And then I'm just doing pure logic, right? So the purity comes in when I don't care what the premises are. I don't care if they are true or false. I don't care, because if the premises are true, the conclusion's also true. Not that they're actually true, right? That's for the scientists to know. So as logicians, I sit in my chair, right? It's a very comfortable job. If you want comfort, then you become a logician. You sit in your chair. The scientists come to you and they say, well, Michèle, Mercury has these reactions, it does this, Mercury blah, 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 and we want to, do some logic on this and find out, where can I go? Is this valid or is this not valid? So I don't know if they're telling me the truth or not, and I don't really care. What I'm now going to do as a pure logician is I'm going to make my proofs, my calculations, my natural deduction, deductive reasoning, or my tree proofs, or my semantic proofs, or my proof theoretic proofs, whatever it is. I'm just going to generate my nice stuff. And I don't care what the result is either. I mean, the conclusion just follows logically from the premises. And then I hand back in a tray, here's the conclusion that you wanted. Or I might even have a multi-conclusion logic, and I give you a whole lot of stuff that comes out. So I've done my pure logic, and I didn't even know what I was talking about, right? So that's sort of doing pure logic, if you like. But it's not a very comfortable dichotomy. Why? I mean, yes, sort of phenomenologically, I can sit and, I love doing, my natural deduction proofs. It sends me to sleep and it's really nice and everything falls in order. Sometimes I say, oh no, that one's a bit weird. I've got to think, what should I do now? So I get a little bit stuck sometimes, but when I do these things, everything falls into place. I don't even know what the premises are about. It's just if P implies Q and I have Q implies R, and I have P, then I prove R, great. But I don't know what P stood for, and I don't care. So I'm doing sort of pure logic in that sense. But all of those rules were motivated. They were motivated by what implication means. And they're motivated by truth preservation through using the rules of inference. And as we all know, there are different rules of inference, governing especially the conditional, especially negation, but even and has different rules. Mm-hmm. There are logics where, and introduction, it's okay to do it from the left but not from the right. And or is not, it's okay to do it from the, I don't know. And there are things where or introduction is not allowed. But it's just or, it's really innocent. It's just sort of seeing them whole, I know this and or whatever, it doesn't matter. But so even or doesn't escape. So nothing gets to escape in logic. But all of these things are motivated at one point. But what the purity means, I get to forget that and I get to not worry about this. I just push it aside. I do my pure work in a neutral way. I don't really care. And then I go back to the meaningful part afterwards. So there's always a history to these logics. There's always a motivation. Well, not always. Because in the conference last week, one of the questions to one of the presenters was, what's the motivation for this? And the person said, well, because it sort of felt nice or they wanted it. I mean, there was no real substantive motivation, but okay. So that's just kind of playfulness, if you like. So the playfulness might be the motivation. I want, we've got two quantifiers. Let's throw in another one, see what happens. Or let's throw in an infinite number of them, see what happens. Let's try to mix modal operators and quantifiers. Why not? Let's see what happens to the logic. That becomes really complicated. And there's lots of different inference rules. And again, these are controversial. There are different inference rules for this, which are controversial. So none of it is, and what does that controversy do? It asks us to ask questions about the meaning or the philosophy or the kind of problem that we're trying to solve. So this, again, becomes sort of pragmatic, right? Mm-hmm. So we become sort of interested in what's the meaning that's going on. And if you're trying to serve science, what are the scientists trying to do? So scientists do different kinds of things. One of them is to kind of make a map of the chemical space, for example. What reacts with what at room temperature at this sort of within this margin of temperatures. 90% of experiments take place more or less at room temperature under pressure on Earth, right? Air pressure on Earth. a few 10% of exotic ones happen at very high temperatures and so on. So these are the chemical reactions that we all know and love. So, but that doesn't mean that's the whole of chemistry, right? The whole of chemistry, you'd have to find out what happens at close to absolute zero, what happens at very, very high temperatures, what happens when there's enormous amounts of pressure. We don't have the money or maybe the interest to do that, right? Maybe there are things that are more immediately important, such as things that will help medical industry, for example. So maybe we don't get to do all of that. So the map is really small that we have. But that mapping is a type of understanding. What happens when we understand is, again, it goes back to your gut and you feel that, I understand, I get it, all the things are in place, I understand what's going on. That's one thing. You might want another type of scientific understanding is being able to give an explanation, being able to justify, being able to tell a story about causality. What causes this, causes that, and I get to know how the pieces get to be put together. That's another kind of scientific enterprise. Other ones are, I'm being paid by this company in order to find something that will fulfill this role. The company wants a plastic that can withstand these very high temperatures in aircraft, in the engine, that is going to be able to do this and to do that, to direct the fuel, blah, blah, whatever it's doing. So I have a puzzle. I have to produce artificially some new thing. That's my goal. And that's all I want, right? So it's not understanding in that more philosophical sense. It's just solving a problem that they have. Why? Because someone's paying them to solve that problem. So I don't know if that answers your question, but yeah, go ahead, please.
Okay, I understand that when you do this kind of work, it's difficult to have some strict rules. But can you give us some methodological suggestions to work with scientists?
Yeah. Okay, so the methodology is not going to be a logical one yet, right? It's going to be go and talk to the scientists. Ask them, how do you explain this? How do you come up with this hypothesis? Get some data about that. And that might be very particular to the laboratory, to those scientists. Because they form a community and they reinforce each other. And when they hire somebody, it's someone who fits into the group already, right? So each laboratory, they think very differently. And the chemists I was working with, they were also working with a laboratory in China. And they said they think very differently. And they had to adjust to that. So different, even a laboratory has its own community that thinks in a certain way. Some things are obvious and other things are not. And what's obvious to one group is not obvious to another group. So if you're trying to do the upper level logic, how do you unpack the box? That's where the fun part starts. So how do you unpack the box? How do you unpack it in this laboratory? How do they actually do it? Then you try to make it, you have to meet the scientists part way if you're going to serve them. What are they actually doing? They have to recognize what you say back to them. But you don't want to give just a description. You want to help them to become more rigorous in their thinking. So your job as a logician, as a sociologist logician who comes into the community, is you say, okay, I notice that you're really uninterested in buying new machinery. Okay, so let's not go there. Buying a new machine, not part of the hypothesis, right? Any hypothesis that says buy a new machine, because the administrator is going to say that. So you start to find out where are the places where you can negotiate, how do they actually think? So you try to describe how they are actually thinking, and then you start to make it more rigid. So you bring in these rules. So it's a kind of sociological approach to designing a logic, if you like, or picking a, I mean, there are thousands of logics out there. Surely you can find one, if you know a little bit about how to look for them, you can find one that's going to help, right?
Or several at once,
Sorry?
or several at once.
Or several at once. I mean, that's right. Is it actually more realistically, is you're going to hold in hypothesis, oh, there's about 7 of them that serve this purpose so far. And then you might be able to ask some questions. Would you jump this way or that way on this decision that actually tells the difference between the two logics? You know, would you distribute negation over or, for example? I mean, you don't put it that way, right? You give them some examples, you see where they jump, and then you say, oh, they don't distribute over or, and they don't distribute over and. So our logic doesn't do that. So you push some away. So you end up with a sort of class of logics that more or less will. And then what does logic do? It trains us to be more consistent in how we use and, how we use or, how we use negation, how we use if then, how we use necessity, how we use possibility, how we use universal quantifier, and so on. So it's a training that makes us more careful so that we understand each other better, because we're all on the same page on the logical side. And it's catalytic because we're more efficient. We don't have one person doing or as inclusive or and somebody else doing or as exclusive or, right? Or does and introduction from the left but never to the on the right. Why do they do that? That's just weird. Don't do that. It's commutative. You know? And so you teach them, look, you're the odd man out. You're the one who's doing a weird thing with and. It's a commutative thing. Learn that. And so you hone the community in their logic. It becomes a bit incestuous, right? So it becomes a sort of closed group because they're using this logic. So you might want to inject something new every now and then and say, hey, let's think outside the box, unpack the box, or put something new in the box. So you might want to refresh things because you don't want things like the two chat GTPs that are talking to each other. You don't want to get smaller and smaller and smaller and dumber and dumber and dumber. You want to inject something new. But what does the logic do? The first thing that the logic does is if you have this sort of sociological approach to logic, is that you would find out how people are actually reasoning in this group. Describe that, find logics that show this, try to hone it down so it's a manageable number of these things, so you're not dealing with, I mean, for any finite number of sentences and finite number of arguments, there's an infinite number of formal systems that can represent that reasoning. That's too many for a sociologist. So
huge amount.
So you just don't worry about that because most of them haven't been invented anyway. So just don't worry about it. So just, you've got to be a little bit pragmatic at that level. So just take a few that you think are sort of reasonable. You find out how they jump. Now, if everyone's jumping outside of your choice, and you have to find another one. But so you do your sociology, and then you do a little bit of training so that everybody's kind of on the same page, at least on the logic side, so that we have a little bit of harmony, and then we're more efficient. So that's that little efficiency. We get to move a little bit faster. We communicate more smoothly. We don't have disagreements, at least over the logic. And then we can come up with hypotheses faster. And then, as I said, because it becomes a little bit too inside the same way of thinking, you might want to inject a surprise and say, have you thought about dealing with contradictions by doing this? And it's sort of so sometimes it's good to disrupt the group, and disrupting people at a logical level is actually politically fairly neutral most of the time, although I've been learning that there's a sort of feminist logic and things, so there's stuff that is not maybe completely politically neutral, but you can present it in a relatively neutral way, just as a disruptor, right? As a let's refresh, let's rethink a little bit. But we do it together. So we train this new way of thinking, say about the necessity operator, about the possibility operator. What is let's open up the necessity space, right? It's not necessary that we confine ourselves to what it is that the administrator will give us in terms of money. Maybe we go to industry and we say, hey, would you be willing to fund us to get this new machine? What would it take? Right? Is it worth it? So then we're thinking outside the box, or we put something new inside of our context box. Right?
And in this line of thought, as a sociologician, you need to be expert in the area.
Yeah, you become a sort of, well, look, I'm not going to be the scientist. I'm not going to be able to put on the lab coat and have the same, because I don't have the same experience as they have. I might be able to suggest something quite good to them because I'll be thinking in a different way. So that's why it's quite good sometimes in teamwork. It's quite good to have somebody who thinks in a very different way from everybody else, because sometimes they bring something original that's good and that's fruitful. So you might become an expert in that sense of something new, but chances are no. Generally no. But because you're doing a different project, you're not doing the science. They are doing the science. Mm-hmm. You do have to learn something about it. You do have to learn the vocabulary a little bit. Mm-hmm. So you do have to know what an enzyme is, kind of. Because I asked my scientist, are they alive? And he said, oh, that's an interesting question. Because they can move. And they do move towards a sort of food source, but they don't have a metabolism themselves. And so there's reasons to think that they're not alive, but they're in motion. So, okay. So it's actually one of those edge questions. What does alive mean and why does it matter? Right, is really the question. So you do learn lots of stuff. So if you're going to do this kind of a logical enterprise, then at least go to a laboratory where you find it interesting what they're doing and you want to learn about it. Yeah. That's a nice question. I hadn't thought about it.
I have just another one, but if someone else wants to have okay. Well, once again, if I understood correctly, the context boxes are proposed as part of possible explanations for unexpected results. Mm-hmm.
Yes.
In some scientific practice.
Good.
Now, you have emphasized that such contextual possibilities can vary widely, as they heavily depend or rely on each scientist's subjectivity and social dynamics and such. Now, my question is, what will be the criterion or test protocol to find out if your proposed context box is the right one?
Okay,
Could
good.
So that after unboxing, say context as premises, then the unexpected conclusion now follows deductively?
Deductively might be too strong.
Okay.
It might be inductively more.
Okay.
but there's a reason why it's open. Okay. And it might take a long time before you find out what's inside.
Okay.
And you might need to put new things in, maybe from another scientific discourse.
Okay.
So what's in there is there's obvious things to look at for you. There's obvious things to look at as a collective team. What's obvious to look at for you might be different from what is obvious for someone else to look at. And you might not find what's going on. You might not find an explanation for generations of science.
Okay.
And that happens. Now, eventually, the idea is that how does science advance is that we find out what counts as a good explanation, right? What is in that box?
Yeah.
And does it then follow deductively? Well, you can give a very tight explanation now. Tight rather than deductive. So it might be by induction. So it might need to generalize at some point.
Yeah, I'm trying to see if I can reduce the test to some sort of
It would be beautiful if it were deductive. That would be the greatest bit, but it's not necessarily.
to a severe test a la Popper.
Right. So that would be great.
Yeah.
But you don't always know. That's the problem. You don't always know. So what counts as a falsification is not always obvious.
No.
Yeah, it's not necessarily falsificatory.
But or what counts as a solution is not always obvious.
Okay.
Again, because there's a lot of context going on.
Mhm.
So and you might not need, so there's a lot of stuff that you don't need to know about. And there's a lot of stuff that you don't bother with, but you might need to bother with, so you might need to think outside the box. That's why the box is
Yeah.
quite good. And you might need to try to put something else in and say, oh, yeah, if I do think about this aspect of the context, it starts to make more sense. It starts to be meaningful. I start to understand why this thing was unexpected. The curve isn't the right, I was looking at the wrong curve. I was expecting things to follow this curve and they're not. So let's just change our conception of what the curve, how to represent what's going on. So it doesn't, that did take some thinking outside the box, outside how the scientists would normally think. And it was an act of brilliance to think that way. It was really fast, right? They did it really quickly, which is great. And that doesn't always happen. I don't know if that answer. I mean, it's a kind of moving pieces answer.
Yeah. But when I use the criterion to discerning your proposed content for context as additional premises is really explanatory. It's if then the unexpected conclusion came out more probably given that context,
Right.
but without the force of a deduction.
That's right.
Okay.
That's right. That's correct. Yeah. So it's a little bit non-monotonic, if you like. So you can add new premises and you get new information.
Absolutely. Yeah.
But that doesn't make it non-deductive yet. So that doesn't make it inductive in the scientific sense, right? So induction inside. So there's a funny edge there, right, where things are moving. That it's delicate, and I think that we can probably. And then there's all the statistical reasoning too, right? So and how you count the statistics is a subtle question. So there are different ways. Yeah. Yeah, please.
Well, thank you for your talk and this time answering questions. Maybe you spoke a bit about this before I arrived, since I arrived a bit late, but I wanted to see if you could say a bit about like your points of agreement and disagreement with Cellucci, I think is the name of it.
Yeah, Cellucci, yeah.
Because some of what I saw in the like in your presentation, like quotes, I think, had to do with like he seemed to be railing against a bit like axiomatic logic and like classical logic and so on. And usually when I see like these sort of like proposals to move away from classical logic into like other special logics or so on, they do have like this underlying like program of some like even replacing classical logic in domains where it's very well established, like mathematics and so on, because it seems to be inadequate for some reason or other. But I'm trying to understand the proposal, and I didn't quite get that, but rather like just a proposal for a new like way of thinking about like maybe like field logic or something, you know, like I don't know, like applied, I don't know, but because for example, when you spoke about complex systems, like eventually it just anchors back down to classical logic, right? Like you have like mathematical machinery, which just, you know, builds from a classical axiomatical base, and eventually you get like tools refined enough to deal with like systems, you know, like non-deterministic systems, like, you know, but underneath the non-determinism of those systems is still like a classical way of thinking about, for instance, like mathematical chaos, which is, you know, like classical. You know? So, like I wanted to ask you about like agreements and disagreements.
So this is actually a question that's in debate right at the moment. So it's a live question about rather than underlying logic, let's talk about the meta logic or the meta reasoning over a logic. So many paraconsistent logicians, some, not all, some constructive logicians, their meta theory is classical. Why is that? Partly because we're trained in it, partly because we feel familiar with it, partly because at that level we think it's okay or it's correct. Other philosophers will say, no, if you believe in constructive logic and your reason is that you should be preserving knowledge from premises to the conclusion, then you had better reason the same way at the meta level too. And if people are making the mistake, if they're putting that hat on, if they're making the mistake of then thinking classically, they should not. They've made an error and they don't know what they're talking about. They are speaking in ways that are literally meaningless. So that's just that's a philosophical debate that's going on. We tend, just statistically, you're quite right, to sort of at the end of the day, we will tend to reason classically. But that, when I say tend, I mean statistically. There's no reason to think that that's correct. So how you recognize correctness that's not a statistical thing. We're not talking about convergence of this many people at this many sentences doing their inferences are reasoning in this way. Rather, correctness, then you need a perspective from which to decide that. And you're going to end up begging the question, you'll be doing circular reasoning at some point. So the question is really about what is your motivation and what is the role that is going on at these different stages in your reasoning, these different levels in your reasoning. The role might be perfectly good, perfectly answered by classical reasoning, but it might not be. If it's knowledge preservation, then no. Then you need a constructive logic. If you still have contradictions and if you want to be tolerant about inconsistencies, then you're going to need a paraconsistent logic. So if you think that you're in a trivial domain and you don't mind that, then you're going to need some way of navigating a trivial domain if you want to do reasoning that looks like reasoning to anyone else in the world. So it's really, it's a deep question. It's not a simple question. Bears thinking about and sensitivity towards.
Just to follow up for me, like, if I understood you correctly, like some of the worries that are behind like this research have to do with like the like ultra specialization in like academic domains, right? Sort of lose sight of what the connections might be between what you're working on and what other areas. But the thing that sometimes worries me about like moving away from like more classical, I don't know, like frameworks
Mhm.
is that I feel that it is sometimes precisely the like unified, like sort of lingua franca, sort of classical frameworks, the thing that allows ones to see connections between like disparate subjects instead of
Okay, right, good. No, that's a fair point. That's why I find it's a little bit political. So why choose a classical framework is because we can all we're on the same page, and we can all recognize what each other is talking about, and at least that question's been settled for now, until you have an anomaly or you have a problem. So it's a good default. Why? Because we're all trained in it. And that's how things are written, that's how the texts are written, that's et cetera, et cetera. So it's a good default. And it's a look, when you're doing original work, you don't want to have too many moving pieces. You don't want to surprise people on too many fronts all at the same time. So keep some things stable. Surprise them in one place. Then once all of that has sort of settled, you can now surprise them in another place. But don't surprise them on 4 places at the same time. Then they can't follow you anymore. So there is, you're absolutely right. In terms of lingua franca, yes, that should be your default mode. And if you find that it's not adequate or there are good reasons not to have it, then you take some time to explain and you have to justify it because it's going to hurt, right? People don't like to learn another logic or another way of thinking. That takes messing with your brain, and that's hard. And people are intellectually very lazy sometimes. They're very active in some ways, in some areas, but if they're not used to playing with logics, and you ask them to change their logic, you're going to get lots of resistance. That's just emotional, political, psychological, whatever. So just be aware that you're putting up a battle if you're going to try to go non-classical in a rigorous way. But sometimes it's worthwhile. Does that answer your question? It's a sort of almost political answer to you, or
maybe just one tiny follow-up.
Yeah.
I was wondering when you were explaining like the box notation, like to me it sounds like it seems very similar to like flow charts, like from algorithms and computer science, which to me they fit very neatly with classical logic. So I was thinking like if there was a way of thinking of these tools just as like extensions or refinements of classical logic rather than alternatives.
Yeah, so it depends on what you're doing. So extension would be that you can do more stuff than you could before, right? So, and it's non-trivial to add, say, analogical reasoning to classical logic. It's non-trivial to add modal logic to are you going to do S5 or S4, and then how's it going to fit with the quantifiers? It's non-trivial to do it. The complexity increases exponentially. So and it's fun to do. So you do want to do this, and you want to keep it as straightforward and as fitting the situation as possible. You want it to be as slick and efficient as possible as well. When you need to include things that you can't get to from the classical logic, you want to extend the classical logic. That's correct. So here's a weird thing, right? Is that they tell me that classical logic is stronger than intuitionistic logic. It's stronger syntactically. There are more things that you can prove. There are more results. They're all infinite results, right? So Hilbert's Hotel, so there's actually not more. Or Cantor, in Cantor's infinity, there's actually not more. There's the same number. But nevertheless, if you take a sort of random sample of a finite number of these things, there's more things that you can prove. Why? Because you're allowed certain moves that you're not allowed in intuitionist logic. There are certain rules that are more liberal. Okay. On the other hand, semantically, intuitionistic logic is actually richer and more flexible and can get you a lot more results than classical logic can. So if you're extending, are you extending in the semantic level or at the syntactical level? So it depends on how you recognize the extension. So even that's non-trivial. So I mean, but it would be easy to say, look, you're reasoning about this, and now you want to talk about possibilities or counterfactuals in your science. If I were to increase the temperature up to this, or if I were to increase the catalytic medium, the thickness of the catalytic piece that's in the fluid, would this actually increase the speed at which the substances changed? So then you're thinking about you're thinking about possibilities. So you might want to add in a possibility logic if that's actually doing some work for you. Which one do you choose? So you choose S4 or S5. Which one is stronger? S5 is the strongest one because you get the most stuff. Everything's connected. But you lose on the semantics because some things become kind of meaningless because everything is connected. So there's no discernment anymore. So it's stronger in some sense. It's not strong in another sense. It's not strong in terms of discernment. It's maybe less efficient, because now your possibility space is opened up too much. So strength is also and best explanation is also it's not innocent. Okay.
I think we're over time. If there's nothing else.
Okay, no, it's okay.
Yeah. Well,
Okay.
Thank you very much, Michèle. I think it's time for an applause.
Well, thank you very much. And as I said, it's a great privilege to be at UNAM. It's one of the greatest universities in the world, and it's a great privilege that you have to be here and to study here. So thank you very much, and and thanks for your attention and coming out on a Saturday. And that's right. I mean, our university's closed on Saturday.
Not in Mexico. Remember that.
Wow. So again, you're more advanced. So well done, and continue with your program. It's very exciting work. Logic is very exciting, and it's a lot of fun. And philosophy is a lot of fun, and it's necessary. So you can have fun while you're doing something really important. That's the best. So good.
I think there is a major field of work connecting logic and chemistry, for example.
Exactly.
Not just of one logic, but
Exactly.
there is a huge of them.
Exactly.
The problem is where to find the right logic for this problem.
Exactly.
Not for all the disciplines.
Exactly.
Not
No.
for
Thank you,
discipline.
Michèle.
We can use that.
Bueno.
That's right.
Muchas gracias por acompañarnos en esta transmisión de Lógica MX. Gracias a Michèle, friend.
We need more logicians.
That's enough. Gracias, hasta luego.
Who know a lot of logics.
Exactly.